Hi. Here we have a three-phase modular multi-level converter, which is used to convert the DC power into the AC power. So here, for the DC source, we have connected two DC. Uh, you can call them sources, and this one is the neutral point of the DC sources. And after that, we have a modular multi-level converter. This is the three-phase modular multi-level converter, and each phase has four submodules in the upper arm and as well as in the lower arm. Now here, what we are going to do, we are going to make analysis between three popular control techniques. The first one is basically the space vector, so I call it as SV, space vector. So the first one is basically the space vector. The second one is basically the very well known technique is the PWM technique. So this is basically the PWM technique control, PWM control. And the third one is very well known technique that is known as nearest level modulation. So we are going to make comparison between these three control techniques, and using all the three techniques we are going to control this modular multi-level converter, and we'll see that what is the impact of using, let's say, PWM control, what is the impact of using space vector, and what is the impact of using NLM on the output voltage of the modular multi-level converter. So let me run this simulation. So I'm running it for only 0.8 seconds, and I don't need more timing for that. So once this is done, let me show you the control system. So for the PWM, as far as the MMC is concerned, we use level shifted PWM control, where we have a sinusoidal waveform as a reference waveform, and we use different triangular waveforms as the level shifted waveform in order to control the submodule. So the sinusoid will be moving with the frequency of the output, that is the output voltage, and then the triangular waveform will be according to the submodules. So if we have four submodules on the upper arm and four in the lower arm, so we'll have four different references or carriers for the submodules. So I have run this. Let me show you the output voltage. So this is basically the output voltage. So here you can see that this is the output voltage of the PWM. So with the PWM, you will have lots of switching, because it's a high frequency technique, and with the space vector, the mid one is the space vector, and you can see that on the space vector the frequency is or the high frequency components are present, but very little one. And the third one is basically the nearest level modulation. So let me show you the total harmonic distortions for the for all the three waveforms. So we will select this, the second one, and we will set the time as 0.1. We need only 5 cycles and we have a 50 hertz. So this one is for the PWM. So from the 0.1 we are taking the 5 cycles, compute 50. So you can see that we are getting 33.06 hertz, where the fundamental frequency, the component which is higher is our actual frequency, which is 50 hertz. So with the PWM we are getting 33% THD in the output voltage. So if I increase this time, if I make it 0.3 will be 0.3 will be for the space vector. So 33% with a PWM, and let me press compute. So for with the space vector we are getting 22.4% THD, which is less compared to the PWM. Please keep in mind that we haven't increased any number of levels. Number of levels are same. Here number of levels are 5 because we are using 4 submodules. So as per the literature, if you are using, like, we are using half bridge submodule here. So if you are using half bridge submodule, right, so n plus 1 is the output. So we have 4 submodules, so 4 plus 1 will be 5 submodules, 5 levels in the output. So with the 5 levels, the PWM gives 33% and the space vector gives 22.4%. So let us see with the NLM, nearest level modulation. So I'm making 0.6 and press the compute F50. Okay, so with the PWM you can see that the THD is 18.4%. so compared to the PWM and space vector, the nearest level modulation gives more sinusoid output, and the THD is 18.4%. right. So this is the PWM, this is the our space vector, and the third one is nearest level modulation. So we can conclude that if we use nearest level modulation with the MMC HVDC, so the THD will be less compared to the PWM and the space vector control technique. The space vector gives satisfactory result, but compared to NLM they are still not good, and the PWM is not even the, that's why it is not used with the systems such as MMC HVDC with a high number of switches and submodules. So that's all about this video. So I can show you my control system. So we have a PWM generator, we have NLM generator, and here we can see that we have a space vector. So I'm switching it at 0.25 to 0.35 or 45. So this is all about this. Thank you.